Hello, this is Helen Gibson speaking to you from Melbourne, Intrepid Geophysics office. Thank you very much for joining this webinar. It's our second one for 2014 and the title is Introduction to 2D and 3D for Geophysical Modelling. Thanks very much. It's great to see so many have joined. I have put you all on mute. It's necessary now to do that. In saving feedback from my point of view, but I do see the chat area, so please contribute to the conversation and I will answer your questions either now or through the Google group forum, and details will be provided at the end of the session. We're going to try and keep it to below 50 to 60 minutes due to popular feedback. I think that's a suitable length of time for everyone. So thanks again, and now I'll proceed on with today's seminar. Forward modelling allows that from a given 3D geology model built in GeoModeller, we can directly calculate a geophysical potential field response. For example, gravity, magnetics, or full tensor gradiometry components. And to do this, we are wanting to compare a predicted with an observed anomaly. And therefore, what we're doing is validating our model. If the comparison of predicted with observed anomalies is not good at all, then we obviously have work to do. We need to consider that there may be errors or imperfections in our 3D geology geometries and or our rock properties. And then as adjustments are made, we can repeat the forward modelling process and compare again the observed against the calculated physical potential field. Once we get to a point with lots of iterations of forward runs, if the comparison is very good between observed and calculated physical potential fields, then we might imagine that we can stop our work and that we have something that we believe is the correct answer. But perhaps this is also a simplistic point of view. They may be realistic, the geometries and the rock properties, but we need to also consider that and keep in mind that there are possibilities of multiple models in all likelihood, because the solutions have a large degree of non-uniqueness. So it's just as likely that your first selected good solution is only one of many. And that's because there are always variations to a 3D geological model that still honour the observed data in the dips and dip directions and also the contact data. And also there are still more geological models that can reproduce the observed potential field data. And so I introduce early now the topic of next month's webinar, which will be Introduction to Inversion of Geophysical Datasets in GeoModeller. And that will be at a time when I can explain how we can discover all of the possible models using our GeoModeller style of inversion, which is a Bayesian approach, and it employs a Markov chain Monte Carlo series of simulations. What then happens is that all of the plausible model solutions are kept, and then we proceed to do a statistical distillation of all the possible models and therefore come up with an optimum and an understanding of geological and geophysical uncertainty in our answers to do with properties and models that can, by varying degrees, all fit our observed data. But that's for next month, and for this month we're going to focus on forward modelling. I draw your attention to one of the first types of inputs that we have to take care with. It's the rock properties table, and we need to supply distribution laws per lithology, and that's per lithology in our 3D geological model. For in this case, if we're modelling gravity, we're concerned with collecting data of density, and in forward modelling magnetics we're concerned with understanding as best as possible the magnetic susceptibilities of the rocks. These other parameters, heat production rate, thermal conductivities and velocities, are concerned with forward modelling in GeoModeller, which is about forward modelling temperature and forward modelling the synthetic seismographs, which we'll touch on today. So if you see this top diagram here on the right hand side, it's about displaying a distribution law, and what I've shown here by example is a two-modal mix, whereby the population inside one geological unit is bimodal, and 30% of the population has a mean of 2.53 grams per cubic centimetre, whereas another part of the population has a mean here of 2.82. This type of population it's not uncommon to see this. This is where you have a mixed provenance of, let's say, a sedimentary basin which is sourced from two different directions, perhaps, and mixing provenance of detritus. So in forward modelling, we use only the mean of the population in the forward run, and that is either as a mix of a bimodal or trimodal or unimodal distribution, but the laws are taken much more into account and explored during inversion. Just to say something about the forward modelling wizard, which I'm about to demonstrate after the completion of the PowerPoint today. The wizard in GeoModeller guides the run setup, and here we allow to have control over modelling parameters, and for instance we can clone previous run settings so that it's quicker and easier to duplicate something you've set up in the past and then just to make one small change to it. It's a very easy way to proceed with doing iterations of forward runs. Also to say that GeoModeller supports 2D gravity, magnetics and seismic, and in the 3D, direct from the 3D model, we can forward model gravity, magnetics, the thermal response, that's 3D in situ temperature, plus full tensor mag and grav. And the two methods that are employed by GeoModeller and are both available by choice, you can choose to do the computation as a spatial forward modelling method, and this method is multi-threaded in GeoModeller. Also, as an alternative, you can choose a rapid 3D fast Fourier transformation method. Another option available in the wizard is that you may choose to do a property optimization, and this is when you have observed data for all your different rock lithologies in your area of interest of your model. You may have some to a good degree of knowledge and others less well known. In fact, you may be just choosing something off published data for, a general sandstone density, so forth, and you really are guessing. So you need to have a starting observation or some starting properties, and then allow the model to run the property optimization, which is a least squares deterministic search through your starting property list, and given that you already have observed geophysics grids and a starting geology model. So this is a really good way to commence to improve your forward models. So spatial forward modelling, the way it's performed in GeoModeller is that the smooth geology model is converted into a 3D VOC set. There's an observation point which is located at a given height above the centre of the surface of the model, and from this we proceed to calculate a gravity response based on a unit density of one cell. And similarly, you can do this type of response for total magnetic intensity and the tensor components. So once that's done, you store that contribution for each small cell or voxel, and it's stored in a response kernel so that all the computations hereafter refer back to that. And that's the way it's handled. Spatial forward modeling performs a spatial convolution of the density and susceptibility distribution from or using the pre-computed response kernel. And in this way we can handle edge effects at the model by mirroring the geology across the edge, which is one approximation to say what is beyond the bounds of the smaller model. Another way to handle this is to actually build a large model and make sure that all your geology of concern is well within the limits of the model. Now, spatial convolutions are exact as a computation, but they do take a fairly long time to compute. And one reason for that is because every time you change the specific height above the given surface, it's very difficult to, or at least it's quite memory intensive to do that. And so now I'm going to just say how the topography surface is treated in GeoModeller. And one thing is to say that from our smooth digital terrain model, we can't always help or hope to compute the response at every point. It's just not feasible. And so how we handle that is to take the terrain model and resample to discrete elevation levels, similar to contours on a map. And this means that it's handling the computation quite well. And a visual way in which we can actually do this in GeoModeller now is with the use of variable Z cell size. You can see here that we have a possibility to set up three values here which represent the band around the area of most interest, and you can see it's been set up for fine discretization through the topographic level. And so you choose a maximum which is above the height of the highest elevation in your model and down to some area where there's it's fairly deep, and you can imagine that the sources are not contributing overly to the signal. So it may be that you are well down into the basement units, or that most of the signal is known to be contributed from these upper level geology units. You can see that we select a lower band, and at this point from here, from minus 2,000 meters below sea level down below, we're applying a geometric factor, which means that the cells are getting wider with depth because we're less concerned to be dealing with the sources there in large amount of detail. So that's a very useful aspect of the wizard. It's only available in spatial method. The other alternative method is in GeoModeller is the rapid 3D fast Fourier transformation modeling method, and the reference is given here to the original work, and it is a very useful method. It's very fast. It's quite memory intensive. And I do mention a lack of accuracy, that it's not seriously important, but compared to the spatial convolution method, it's worth noting. And so the lack of accuracy is well documented, and for good reason. It's that Fourier methods impose periodicity on the solution and so only provide a measure of the average signal spectrum. To compare the two methods, we'd like to just comment that the FFT results are a good approximation and will reproduce the major features and trends. FFT is very fast, but it's not as accurate for spatial forward modelling, and it's more memory intensive. So we normally would recommend it at the beginning of your workflow when you need a rapid approximate answer, but the spatial method would ultimately give you the accurate results. Now we'll move into the software. So if you could just bear with me. Today we're going to speak about the Brockman Syncline. So the Brockman Syncline is located in the Pilbara region of the Hamersley Ranges in northwestern Western Australia. It's an iron ore province. It's known for its high purity, including hematite. It's hosted in the lower Proterozoic, and the Brockman banded iron formations are mapped here in 3D. What I'd like to say about this data set is that it's from the public domain, so it's controlled by, what you can see here is points of contact along the fault traces, which cut through the limbs of the syncline, and out on the limbs the different banding is constrained mostly by surface data. I'll just briefly show you the stratigraphic pile. So it's mostly treated in one series as a conformable group of sediments in this simple model, which have been folded through the sequence. So without really trying to say too much more about this model, I want to draw your attention to perhaps the geophysical grids, and we can right-click in the background of GeoModeller to display only the lines of the model, taking away the fill at first, and also we can take away the raw data which constrains the model. The geology data and the geology orientation, so that's the contacts and the structural data, can be removed just to clean up the view. And now I'd like to bring in the images of the grids that we're going to have a look at today. The first of them is the TMI at 50-meter line spacing, and I can view it both on in 3D and in 2D. And so we can do that now. I have a block model on the right, which I need to just hide from view right now. And now you can see the TMI image is shown here underneath the actual model, just the outline, so that we can see the effects, and we can see how nicely the geology is speaking to the magnetics. They're very related. You can almost map straight off of this type of image. On the right hand side, if I put some vertical exaggeration increase, you can see this is draped now on the DTM here around the Brockman Syncline. It's really quite a nice image. I can return that, snap that back to natural scale now on the right hand side. So what I would like to do next is show you the gravity image just by hiding from the field of view and then bringing in, this is the free air. And I'm going to place it in 2D and in 3D at the same time. And there we have it. So what I just want to bring back into mind now is that we have had a smooth geology model, and that was available to us. If I hide the grids and meshes now, we can see that the smooth geology is available. to us, but once we begin the computational process to do forward modelling, we're not talking about smooth geology anymore. We need to move into the block model zone. So what that means is we've done a discretization, and I'm just going to hide the smooth geology and show you the lithology Vox set in 3D. Here it is. It's so we have now a sense of different resolutions can be set, and we're ready to do a computation. First thing is to have a look in the physical properties table. So here on the, I've just opened it now, you can see a number of tabs available. So each of these respond to a lithology in our pile. Here on the left hand side, you can see every value that's been assigned to every lithology in the model. And along the top, you can see that there's the possibility to do forward modelling of gravity, magnetics, thermal. Advection is under development, and seismic this is the place where we store all the properties per lithology to be available to the forward modelling solutions. I'll just perhaps dwell a little bit on the magnetic menu here. So what we have is magnetic susceptibilities on the left-hand side, and we also have the possibility to model with remnant magnetization. Just remembering too that our GeoModeller model is a truly located model in the real-world coordinate systems, and so by virtue of that, it means that GeoModeller understands where the grids are. When we import a grid, it knows exactly where it is, and it knows the location in the world of the model that we're building, and therefore it does suggest to you straight up a total magnetic field by virtue of the fact that it stores a model behind here. So all that may be required is to use the IGRF calculator, also available to us, to either change or apply a date that you know that the survey was flown. So that's available to us. So just now to demonstrate, firstly the geophysics menu. Once we've applied, filled up our physical properties table, we have a 2D ability to do 2D line profiling. And so here we are with the menu open, ready to go. First of all, I'd like to do a magnetic computation. So it's a matter of just pulling up the section that's already existing in your project. We can just choose section 1. You might notice the physical properties. You've got a little defined button in here, which means it's telling you it's available. If you click on the physical properties here, you can revisit the physical properties table and make a change here directly inside the interface. The other thing I could show you is to say that you have a distribution population here, which is there's a number of statistical laws that can be applied. Quite often magnetic susceptibilities are known in nature to be log normal, and so we would select log normal. The other thing is that you type in your value and also the units. It's possible sometimes that micro SI is more easy to type in. For obvious reasons, and also you would need a standard deviation, but only if you're going to be using the inversion module. Most often what you need to know is that you're taking forward just the mean in the forward modelling case. And so I can leave this menu now. I'll just maybe briefly to show you that it could be bimodal or trimodal, and when that happens you get the possibility to mix different populations at different ratios of the percentage of 100, and due to time I won't go on and set one of those up, but it's a way to mix the population. So what we're going to proceed to do is browse to the observed grid for this data set. It's the TMI at 50 meter spacing. We'll just leave the number of computation parameters, the number of stations as the default values, but we're going to do a computation surface which is based at 300 meters or above the current topography. And we'll do a computation. This is a simple line profile, and we'll move into, next will be the way in which we can use the full 3D model to compute the response. This is now the forward computed magnetic response upon section 1. And what I'd just like to say is that what comes up immediately is the same range centered for the axis. So you can see on the left-hand side is the axis for the computed anomaly. On the right-hand side is the measured anomaly. So it's approximately the right range, but there are some differences we need to work on, and so our next forward model run will be attempting to improve the properties and so forth. So the idea here is to work in 2D before moving into the 3D, so that you can verify along a number of lines that you are correctly modeling before you move into the more complex situation of modeling 3D. If you click on the background, you're able to change to independent axes. You're also able to change to a common axis, and by swiping with the mouse you can also enlarge and zoom in on areas of interest within the curves. So I'm going to leave that one now, and the next thing I'd like to do is do a computation of seismic. So this is also, we'll also aim to do this on section 1. One thing to note too is that down the bottom you're able to show the discretized geology as a representation of what it is on section 1 in your model. It just helps for a visual. And it also allows you to remind yourself, what is the discretization scheme? Is it coarse or is it fine? So in this case it's quite coarse. Now just going through to the choice to do a seismic forward model. Let's produce something from some velocities. Again, you can access the physical properties table right from the menu here. By double-clicking on a field, you can access the place where you type in a velocity and a standard deviation about that velocity. Again, bimodal and trimodal are also available to us. So in setting up the run, I'm going to increase the number of samples. 3,000 is quite a high sampling, so that's coming in time, the sampling per meter. Also through the spatial variation of the sampling, I'm going to increase that to 250, the stepping in X and Y. And for the frequency of the sampling, I'll leave it as the default, which is between 10 and 40 Hertz. If some of the properties are missing from the table, you would not see a defined word there in green. You would see partially defined or not defined, to remind you that there are still some gaps needed to be filled in your physical properties table. So we can tick the box to compute seismic and commence to do so. I did have a question come up which says, how did I get the different physical properties for each lithology? And the answer to that, thanks for the question, it is based on published, in this case for the Brockman Syncline, there is some published information available. But failing that, if you need to do a literature search, you may have the possibility to put in some standard published values and then begin to do iterative forward modelling to improve your guess at what the more realistic values of the physical properties are for each lithology. So if you have a starting point because of measured values, then that is a very good thing. You may have only some of your lithology units have measured data and others you have to work out based on published values. So here now we've got our synthetic seismograph, which is produced for the line section 1 in our model of the Brockman Syncline. And as you do a mouse wave across the synthetic seismograph, you can see 3 values. You can see the first value is just a coordinate in the local section, in the UV section. As I'm going to the left, it's increasing. The middle value is two-way time. And you can see as I'm going up and down, the two-way time value is varying between 0 and 2.75. And the last value in brackets is saying something about the amplitude. And so only it's actually also represented in the scale above, which is from black to white through the amplitude. Down below we have, as I said before, the representation of geology in 2D, and the 3 values there with the mouse wave are U and V, which is another way of saying the X and Y value on the local section. And the third value is the other dimension away from the section. I'm answering a question, is the blocky seismic model not going to give you all manner of horrible? Yes, it is fairly horrible, I do agree. It's poor resolution, and I don't want to say too much about the modelling here at the Brockman Syncline. Today I'd like to mostly display to you what the tools can do. So I apologise if there's not a lot of high resolution work here, and also these are not true velocities because I don't actually have any published velocity values for the Brockman Syncline. There's some reflections happening here which are just repeating, so again it's really only just to show you that it's possible to do a synthetic seismograph. And if you had, which I don't have in the case of the Brockman 4, but if I had a seismograph to compare against, then I could really do some good work here. It's just to show you the tool today. You can actually save the images, and that is something that I was able to do with the bottom button, and so you can save out a TIFF image or anything you need to do. So I've done a few of these runs today already. And now I'd like to move on in our remaining time to show you the full 3D modelling. I'm going to use gravity, and if you could just bear with me, we'll just go through now and just remind ourselves that we've loaded densities into the table of physical properties. And so here I might add that more typically you'll find that densities will have a normal distribution in nature, and so again it's important to think about this law that you're applying, and it becomes even more so important once you're doing inversion and less important with forward modeling, because although there are other options are available, we'd probably be just usually taking the mean ahead as the value for everywhere throughout each one of these lithologies at one time. Okay, so now we're going to go under the Geophysics menu to 3D Geophysics, forward modeling. And the wizard takes us through. It's fairly easy to follow. So let's commence now. The idea is to pick the field that you want to compute. So you might see that we have vertical gravity available to us. We have gravity tensors, and we have each of those separate components, and as well as that the full tensor combined. And the same for magnetics. So there is a lot available to us. I'm not going to talk about full tensors today. I think I would probably rather leave that to someone else on another session. So if you're interested to hear that, if you could email me and I could line up one for later in the year with another presenter. So the idea here is to just realize that the wizard is choosing a name for us. It's choosing case 2 because that's the next one in line. It actually is going to store every case as we proceed to make a run. So all we need to do here is tick GZ because we want to compute vertical gravity. The second page of the wizard allows us to search for an observed grid, and you can still do a forward model without having the observed grid, but in this case we do have one, so we're going to browse to it, and in this case it's a free air grid available to us. We're also going to choose the clearance, which I believe to be 300 meters. It's an aerial grid. Conxie has asked me a question. Why do you use the free air instead of Bouguer? Because the MGT is resampled, then less accurate. I wonder how this influences the final results. It's a good question, Conxie. I'm going to actually leave that to my brain's trust, and perhaps we can see the answer up on the Google group forum. I have to admit I'm a geologist, I'm not a geophysicist. Free air is the rawest data set, of course, that's available to us, and that's just what I'm working with today, but as to why, I'll have to leave that to the experts. Okay, so we're going to tick the box to say that we want the computation surface to be above the terrain by 300 meters everywhere. We also have the opportunity for constant elevation, but also for a real drape grid, which we can browse to. And if I show you what's available, there's a list of file types here. So if you had the survey from the plane and the correct positioning of the drape by a data set, you can just access it here in any of these grid types. And these are the ones that are supported. Today we're going to use topography that's already in the model. Maybe Alan's actually answered your question, Conxie. Alan's saying that free air is faster and includes the topo in the model, which is where it should be. Well, thanks, Alan. That helps. On our next page, we get to see the way in which we're going to discretize the model. So in the background, I've kept a block model up for you here, but that's an old run. it's a different discretization scheme, because now we're getting to choose a new discretization scheme because it's a different case. So I'm going to choose, for the resolution of X and Y, I'm going to choose that there's 80 cells in each direction. And automatically it gets refreshed just to the left here as to how many meters is represented by the number of cells becoming 80. And so this is just a simple computation that's broken up from the size of the model, which is it's set in a wireframe which can't actually be changed very easily without reloading a project. But what you have is a set model size, and we're discretizing it by 80 units in X and 80 units in Y, and the corresponding meters are 212 and 250. Now I'm going to just show you that here on the page we're talking about having a spatial forward modeling method represented. You may remember discussion about that, that in the PowerPoint I said that there was a discretization or at least a sampling interval whereby you could say that you're going to, how well you're going to represent the DTM. And so the smaller this number, the better. But also at the same time, you're increasing the amount of memory that's needed to make those, make a change in the vertical sampling interval. At the moment, it's quite low, but we want to decrease the number to 15 from 150, and that's already taking it up to 91 megabytes. If I increase it to 5 and even to 1, there's a very large memory requirement to do that and to represent the topography very finely. So in fact that's just one way to do it, but if we do what is offered to us is the variable Z, and I'm going to tick this box. As soon as I do, the option to do the vertical sampling interval is no longer valid, because we're going to choose a better method or a different method in which to improve our representation of the DTM. So this is going to allow the variable Z resolution of the voxel model, and it will be set up on the next wizard page. Just while I'm here, I'm going to show you also, if I tick the box here, it says Run Property Optimization, and this is supported for the optimization of density from GZ, and also the TMI is supported, but you can't actually support. We can't actually support optimizing remnants, unfortunately. So moving on to the next wizard page. Let's have a look. I must have clicked something. No. I see it needs a number there that makes sense. Let's have a look. Okay, it didn't like me to have nothing in the vertical sampling, so I just needed to refresh that, and we're going to proceed to look at the variable Z option on the next wizard page. So what you have here is the ability to set up a band, and the top 3 cells here are letting us set up a band where we can have high resolution into our discretization scheme. And below that we'll just have what was existing before. And also I want to say that this is just talking to the Z dimension. So on the previous page we set up the X and the Y, and now we're setting up Z. The thing to think about when you're setting up a band is to know the highest peak in your topography and just to go slightly above it, and also to have a think about, in terms of geology, where's the likely sources of your response that's going to produce the gravity anomaly? In this case, I'm thinking that these important units here of the Brockman ion formation are going to be contributing quite heavily to the response, and so I'm going to make sure they're covered in high resolution. And likewise, if you had some thin bodies, you would make sure, if possible, to have them covered in high res. But once you get down into the basement units, it becomes less and less important to have the cell size well described, and so at depth we can let that go out to quite a big cell, and that saves us on computation time, which is very useful. You can see now that I've set the top layer to be at 700 meters above sea level, and the bottom of the band to be at minus 250 meters below sea level. So it's going to be also in meters. I'm setting a cell size of 25 meters, so that's quite fine. And you can see the response already here. The fine grey ticks are showing us that that scheme has been applied. Next is to apply what we need for the lower units. There's a possibility to put in a geometric factor here. So what that means is you're able to increase the cell size at 10% for each cell you're getting deeper. That's why I've set 1.1. Then finally you get a little report down here. It's just telling you that you, in the top topography part of your model, there has been 38 levels of discretization, and down low it's only 4. And you can see, you can even count the 4 cells, and you can tell that the bottom one's expanded. Okay, so now we're ready to go, except that I also want to say that it's a dynamic model here. So if I take these and slide them left or right, I can change the view in X, Z or Y, Z. And so as I do that, you can see that there's I can make a check. Here's an important place to check. I would have thought that it's important to see what's happening around topography like this. So if I also drag onto the page, I can zoom and see how well I'm going to represent my topography. Of course, the aim is to match the black line here, because this is real topography, but the computation height is going to be at the top of the middle of each cell. So the finer I can get the resolution to be around topography, the better I'm going to match the black line, which is our real topography. I can zoom out and I can change the axes as well. Okay, so that'll be all we need to do on this wizard page. And proceeding now, the next thing to do is to include the border effect is obviously quite critical to be able to get rid of the edge effects. Also, I want to point out here on this page, there's a possibility to put in another type of density initialization. What we've done by default is to select the mean of the distribution law. So if you remember when we were talking about that properties table, I was saying that the computation is just going to be made for each lithology based on the mean value of density. But that's not quite true, because you have a chance to do 2 other options. One is to make a random distribution available. What that means is it will sample from under the bell-shaped curve of these normal density distributions, and in doing so it can fill in a random way a variety of different densities, as long as it's allowed within the law, for each lithology. The other choice is to choose from Voxet. Now this becomes very useful to us in our repeated forward modelling, because you can access a customized distribution of densities in a Voxet that matches our lithology Voxet, and these are easily created. I mean, they are actually an inversion product, but if you have another way to create them, then you're also able to bring them in here. And if I browse on that, you'll see the type of file type we're after is typically a GoCAD Voxet, but there's some ASCII Voxets available to us as well, and different UBC meshes as well are supported to bring in for this customized distribution of densities. We're just going to set mean law for the moment, and as in terms of knowing that we have we're working above topo, and we're also using free air, it's really meaningless to have anything, I think, other than zeros here. But of course, a Bouguer corrected data set, you'd be wanting to match the Bouguer correction and so forth. So on our next page, sorry, I'll just remind you, it's possible again here to highlight and then to choose to vary the density at this point in the wizard as well. So going on to one of our last pages, it is our last page, we're going to be able to choose interactive or batch mode. A batch mode will keep job files for you so they can be rerun or run in batch. So you have the choice there. The other thing to do is to choose the number of cores that you want to have involved in the computation. And so 8 has been recognized here because the computer I'm using has 8 CPUs. But if I'm allocating other tasks to other cores, I have the possibility to change that here. And this is available to us because this is a multi-threading, this process is able to be multi-threaded. I'm going to cancel this because what happens is that it will take quite a while to compute that high resolution. When I say quite a while, it could be 45 minutes, and I don't think anyone would like to be that patient. So I'm going to cancel that job, but what I want to do is to let you know that every time that you do a new case, they'll be saved. So under the Geophysics menu, you go to 3D Geophysics, and go to the Results Explorer, and each of your cases is preserved. So here is my run from this morning, and you can see there's just the one case in here which you can open up, and everything is preserved in terms of the settings that we've just been through. So in terms of the extent of the 3D model, the references that we put in, even if they're not used, because of course we're modelling forward gravity, but all of the settings are retained regardless of whether they were used. Per formation, you can see everything from the physical properties table is there, including the things that we didn't use this run. And the observed fields are here as well, plus the clearance and the sampling and the error. This is all available to us to look up and to be retained as a record. Once you are back, once you have come to this summary screen, you'll notice that here on the top left-hand side, it's a representation of our observed gravity grid. And you can see the dynamic range here is, or at least the range of the data set is -3 to plus 53 milligauss. And you can see the trending here of the limbs of the syncline. In the center here, it's our computed response. So you can see that we have some work to do still. Our model is cheers, Alan. Thanks for joining. I'm just continuing on to say that this is the computed model, and it has a range here which is before any type of regional removal of any regional trend has been taken out. And so the lower line of results is reserved for detrending. But just to continue on, the top right-hand side is the misfit. It's the observed minus the computed grid. And so we have a misfit which isn't particularly good, because over here you would like to expect that we're going to have a very even color of representing a very close match of observed minus computed. So what we're able to do, just moving down to the bottom row, is to choose to do a detrend. If you set the degree as 0, this is equivalent. This is doing a DC shift. And if I solve that and apply, you'll see that now it says it's our computed response with the detrend. And so it has brought down the mean, you can see, compared to the initially computed response. And here on the right-hand side is the new misfit. This is really the range now that we need to work to get down to 0. So we're hoping this misfit, once we've done some more work to improve this particular case study, it's just new for us, to be working and improving the fits. We would like to get this all down to the low value of about 0. And you can see you can use your mouse here to go through and see where you need to do the work and to what values are actually everywhere here in this grid. These grids are kept, by the way. They're written out to the file of the model, and so you can examine them later. The other thing I'd like to say is that here under our grids and meshes, you have the possibility to import, and you can see I've already done that, but if I say here that I would like to import my results, we have just the one case available to us, and if I do that, it's going to delete the first time that I brought it in. But you can see here it's overwritten because it knows that it's already brought it in before, but it actually does bring automatically for you the results, and they're able then to be seen directly in the viewers. So this is our computed response in terms of gravity, and we can also show the view of the observed gravity at the same resolution. So this is what we're trying to achieve, and the previous one was the calculated gravity. I think I would like to leave the session here. We're trying due to feedback to keep it within 1 hour. So if I'd like to just draw your attention to what's available on the YouTube channel, we're going to be keeping all of these available via this website. Maybe you'd like to capture on screen now. You can see these. Here's our YouTube channel. So today's webinar will be posted up on there. Plus, what else you might like to do after seeing this webinar is to join our Q&A, our question and answer Google group. So first you'd have to log in and to create a Google account. But then afterwards, if you join this address, you can particularly have questions about the February webinar and also the January one of 2014. And finally, if you would like to take a free 4-week evaluation license for GeoModeller software, you can read here or take a screen snap to to follow those instructions and go to our web page where you'll be able to download GeoModeller, the first maintenance release. And when you launch and run that software, you'll find that the license manager will come up with a license request, and all you need to do is fill out the 5 lines of your details, contact details, and send us a request for a license, and we'll happily supply that to you. Together with support if you'd like to email questions as you're using the data. And don't forget there are inbuilt manuals and tutorials available, which by the way get unpacked as soon as you download the software and even before you have the license. So you have a possibility to read ahead of time to know which tutorials you might want to attempt. So for now, I'm going to unmute all and say hello again to everyone. And now that I can hear your voices, if you have any questions, please go ahead. I think it's also a good opportunity if you'd like to think about your questions and then type them via our forum. I'd be very happy to answer them there.